So 0.01 Coulomb.
Just a moment. Point 0.01.
So 0.01 Coulomb. Sorry, sir, 0.1 Coulomb.
0.1 Coulomb.
Yes, 0.1 Coulomb. Any questions? Let me know. This would sound like conservation of mechanical energy that we used to apply in work energy topic. But then delta U here is not mechanical potential energy. This is electrical potential energy. So strictly speaking, M word won't be applicable here. M alphabet giving mechanical word. We have got two identical particles, QM, QM. Q is given, M is given. Distance between them initially is given. Since they are identical, they will repel and they run away from each other. Finally, when the distance between them becomes huge, then what is the speed of each one of them? Speed should be same due to argument of symmetry. Again, when you deal with conservative field, instead of calling this conservation of mechanical energy, you can now make it more general, not just mechanical. You can say whenever there is conservative field present, whether it is some mechanical field or non-mechanical field, as long as it is conservative, it could be springs, it could be due to spring, it could be due to earth, it could be due to charge. As long as it is conservative, this law will hold good. So delta U, final U, minus initial U, final kinetic energy, we are talking about the system, minus initial kinetic energy, everything that you need to know is given.
— 600 meters per second.
V. Let me see. (600 meters per second).
Sir, why did you take half mv square twice?
Because there are two masses, both of them are going with speed v. Any other question or we move on? Fine. Earlier I had mentioned that finding potential could be easier in many situations than electric field because potential is scalar. So if for those situations, if we can first find the potential, and then if we have a relationship between field and potential, allowing us to find field from potential, then that can be very useful. So what we are going to discuss now is the relationship between the two things. One is a vector, other one is the scalar. And we will discuss both the things. Knowing the potential, how can you find field? And knowing the field, how can you find the potential? Consider some point where the field is E. That field could be due to some charge configuration. In that field, we are moving charge small q from this point to this point. This point has position vector r. This point has r plus dr. At this point, potential is V. As it moves, work will be done due to this force QE. And that work is, because the distance is little, I'm using dW. QE dot dr. We want to relate field to potential, so we must reach potential energy. This is dWc, conservative. So it should be minus du. And dV is du by q. So this we can take this side. E dot dr will be minus dV. That's it. Look at this. V on one side, E on the other side. So we should be able to get what we are looking for. Let me write it this way and then integrate. Initial to final, initial, final, final. So V at R2 minus V at R1. Now V is not a vector, but R2 is a vector, R1 is a vector. V at R2 position vector minus V at R1 position vector. That's it. That's a very useful result. Very useful. This is what I would recommend that you memorize, though we can make it look simple by taking one of the two as infinity. But this is the one you should remember. If we want to talk about V at a point, we can take R1 or R2 as infinity. Let's take R1 as infinity. In that case, potential at infinity is 0. This becomes 0. So if that becomes 0, V at R2 is now you can drop the subscript 2 and it will just become V at R equal to minus infinity to R E dot dr. I will delete 2 here itself. So while this may look easy, this is the one that I would recommend because sometimes a twist can be given in the question that reference point is not infinity. So that way this becomes the most powerful way to handle. Now this is useful if you want potential or potential difference knowing the field. So knowing the field, finding potential or potential difference. This is the way to do it. How about the other thing? Knowing potential, how does one find the field? Let's begin from this point. Up to here the discussion is same. E dot dr equal to minus dv. Left side 2 vectors, right side scalar. Write this vector in terms of its components. Same story here. Taking dot product should be very easy. Minus dv. At this stage, it is not looking very friendly. We want field from potential. But now we will introduce partial differentiation and things will become very easy. You see, when we say field in general, field due to some configuration, that field can change from point to point. So when we say vector E can depend on X also, Y also, Z also. Point to point E can change. Now, when we talk about partial differentiation concept, X is changing, Y is changing, Z is changing. In place of changing all of them simultaneously, let us change one at a time. One at a time. Supposing we only change X, keeping Y, Z constant. dy is 0, dz is 0. In place of d symbol, we will use partial symbol or dou symbol. Now we have got something very useful. Potential also depends on the point, may depend on the point. Potential is a function, V. V is a function. It can depend on X also, Y also, Z also. So differentiate that potential function with respect to X, keeping Y, Z constant, which is a very easy thing to do. And you will get Ex. And then change Y, keeping X and Z constant. And when you do that, dx is 0, no change in X is allowed, dz is 0. you will get Ey partial y, Ey partial y or dou y equal to minus dou v. Finding Ey by this type of differentiation is extremely simple. And in the same way, you can find Ez. Ez would be minus dou v by dou z. So you can find vector E also, Ex I cap, Ey j cap, Ez k cap, and you know its mod, magnitude, right? So we have got two very useful things, knowing E, how to find V, and the opposite. Any questions in the theory part, let me know. Now before we do this problem, from this you can have another unit for E, rate of change of potential. That means volt per meter. Volt per meter is a very common unit, and it is akin to Newton per Coulomb. So both of them are used for electric field. They are one and the same. Potential changes from point to point, as you can see. Find the expression for the field. Now, A is constant. In fact, Y and Z are also constants. Can you tell me what would be the answer of this part?
So y plus z I cap.
So y plus z.
Y plus Z. Unit vector will add later. Likewise, this and this. So if when you are giving the final answer, then you need to have IJK. That's it. Any questions? If you have, then let me know. Okay, now let us take the opposite case. Suppose field is given. We want potential where origin, there is a little twist. Reference point has been changed. So it is not 0 at infinity, but it is 0 at 10, 20. It just says 10, 20, so I suppose that Z coordinate possibly doesn't really matter. We will know when we solve this problem. This is what we want. So this is the general equation. R1 we will take as this. Now let's see why Z coordinate should not matter. Yes, go ahead.
So this 500 volts.
Answer. Let me see. It is 500 volts. E dot dr, that should tell us if Z coordinate should matter or not. Now you can see that, in fact, even Y coordinate doesn't matter. Ax I cap, Ax dx, it is basically Ax dx. R2 I will take as 0, 0, 0. R1, 10, 20, any Z. R1, 10, 20, any Z. 0, 0, 0. E dot dr is Ax dx. ax dx. This is the reference point, so this will be 0. So v 0, 0, 0 minus 0 equal to a is outside, x square by 2. And that's why I was saying even y coordinate is of no use. The limits that you are going to put, they are only on x, 10 to 0. So can you put the values, limits and a also, and see if you are getting 500 volts or not? In the previous question, field was depending on x coordinate. It was changing field. In this problem, field is constant. You can see no dependence on x or y or z. So it's a constant field. Take the reference potential at origin. Find the potential at 2, 2. It looks like a 2D problem. Can you try this on your own?
So if it's minus 100 volts,
Let me see. Minus 100 volt. If anybody has any questions or problem, then let me know. Okay. As you can see from here, field has to do with rate of change of potential. We have talked about Ex, Ey and Ez. In fact, Ex, Ey, Ez are the components in X direction, Y direction, Z direction. We can find the component in any direction. Look at this. Component of field in any direction. In fact, this is a very useful relationship. This can be obtained in no time with this one. This is easy to remember also. This is also recommended. Now I'm interested in component of E in any direction. If I choose that direction as dr, then E dot dr will be E dr cos theta. Basically, E cos theta will be the component in that direction. So how do I get E cos theta? I just need to find minus dV by dr. It's like this. Suppose field is in any direction at a point and you want its component along certain direction, making theta from it. Draw a line making that angle with it. In the direction you want component. So this will be this direction will be E cos theta. I mean, rate of change of potential in this direction with appropriate sign will be E cos theta. This is like dr vector. Go from here to there. See what is the change in potential. Say this is VR. This is V R plus dr. So minus dV means final. Minus initial. dV by dr it should be. Minus sign is there. VR, V this. It's like fall in potential, rate of fall of potential it is basically. Rate of fall of potential. Component of E in this direction is rate of fall of potential. When we say fall, it is initial minus final. So suppose you want component in this direction, find fall in potential, this minus this, divide that by dr. This is dr. This distance is dr. So now you can find the component in any direction, not just x, y and z. Now that also means that instead of going in this direction, if we go in this direction itself, then we know the field. If I take 2 points here, VR and this at dr separation, then theta will be 0, cos 0 is 1, I will get E itself. So what is E? If you move in the direction of E by dr, then it is the rate of fall of potential. E is the rate of fall of potential in this direction. Now when I say rate, it is not derivative with respect to time, it is derivative with respect to r. There is another way to look at it. Cos theta is making this side small. If I can maximize this side is maximized, cos theta can be made 1. If I maximize this also maximizes. And cos theta becomes 1. So can't we also say that in some direction where potential fall is maximum, in some direction along which potential fall is maximum, the same direction is the direction of the field. There can be several directions along which you can walk. But if you want this to be E, you should have cos theta as 1. Left side is equal to right side. To maximize this side, you have to maximize this side. And then cos theta would become 1, and E itself will be minus dV by dr. So choose that direction in which minus dV by dr is maximum. So automatically cos theta will become 1. So electric field is going to be in the same direction along which the potential fall is at maximum rate. Potential fall is at maximum rate. Again, when we say rate, it is not differentiation with respect to time, it is this. So how will you tell the direction of electric field? How will you tell the direction of electric field? Just see that direction across which potential falls most rapidly. Potential falls most rapidly. One example that you will understand easily is that of a point charge. You already know the answer for field. If I say this is a positive charge, what is the direction of field at this point? You know the answer. Radially outwards is the answer. Now, let's apply what we have learned just now. Potential formula you know due to point charge. Potential depends on the distance. So if distance is fixed, potential is going to be fixed. If distance is fixed, same everywhere. By the way, such surfaces are called equipotential surfaces across which potential remains the same. For a point charge, they are going to be spherical surfaces, equipotential surfaces. I can draw another equipotential surface at a different r. I've got two equipotential surfaces now. Everywhere same potential, everywhere same potential. But yes, potentials, these two don't have to be the same. They won't be the same. Now look at the rule. Direction of electric field is along that route in which potential falls most quickly. Now, potential is falling. This is low, R is more, right? This is high. So, I know potential is falling. But the question is, along which direction will it fall maximum? Should I go like this? Will that be maximum? Will this be maximum? And what justification, what explanation do I have? The explanation is this. Potential here is some fixed number. Potential here is at some fixed number. So gap between the two is same. Whichever path I take, this path, or if I like traveling more, this path. In all of these three paths, potential difference is same. Right? So I should look for smallest dr. If the numerator is same, if fall is same, then I should look for dr. I want this to be maximum. In which way dr will be minimum? This way, or that way? The answer is obviously this way dr will be minimum. If dr is minimum, this whole thing will be maximum. So the direction of field is along this dr vector. Right? And you already know it is true. Direction of field is this only, radially outwards. So when we have the knowledge of equipotential surfaces, it is possible for us to know the direction of field at various points. So we talked about field lines. How about giving equipotential surfaces? After all, once we have equipotential surfaces, then they also guide us about the direction of the field. So they are also helpful in some cases. Yes.
So why is the potential difference in the three paths same?
Because potential is inversely proportional to R. So if R is same for all of these points, suppose this is 10 volt, it is 10 volt everywhere. And if this is 5 volt, it is 5, 5, 5, 5, 5 everywhere. This point is at 10 volt, this is at 5, 5, 5. So 10 minus 5, 10 minus 5, 10 minus 5.
Fine, sir.
Any other question? You don't have to answer it right now. When the separation between two charges is increased, which types of charges not given? So you need to look at different possibilities. Same types of charges, opposite types of charges, etc. That's your assignment question. We stop now.